All right, we're going to talk just about a couple of greedy algorithms today. One of which is I think almost the most practical algorithm that you'll see this whole semester in some ways. And the other is just kind of a little warm-up. You've already seen greedy algorithms before in the minimum spanning tree context. And basically anything where you can do a local optimization repeatedly and have the global optimization work out in your favor, that's a greedy algorithm. Basically, greedy algorithms tend to be simple to describe, and you tend to get lucky. And you prove that your luckiness wasn't lucky with some theorem behind the scenes that says doing what you thought was just greedy really does work. So every greedy algorithm has some theorem behind it. The theorem's sometimes tricky to prove, sometimes a little more straightforward. They often use induction. This example is a classic example of an algorithm that's a greedy algorithm. It's very, very simple to describe. It has a proof of correctness that's by induction. You can read the proof in the book. We'll talk a little bit about why we think it works without a formal proof, and then we'll let this example go and go on to a very practical example. So this example is one we started yesterday, and I'll put the example back up on the board. You're given a bunch of intervals of time where things are occurring, classes, meetings, and they overlap. This example is directly from the text, so you don't have to write it down. Here are the intervals. The problem, as I said it originally, and it is really this way, is to find the maximum number of different activities that can occur during the whole time period. Here's the way the algorithm works. You start with a first activity and you schedule that. Then you move on to the next activity that doesn't overlap with your first activity. That basically means you look at when this ends. It ends at time 4. You go down to the next one that starts after 4, namely this one. Then you go down to the next one that starts after 7, this one. Then you go down to the next one that starts after 11, and it's this one at the bottom, the 12, 14. So you can get 4 activities, 1 through 4, 5 to 7, 8 to 11, 12 to 14, and your day is filled from time hour 1 to time hour 14 with 4 different activities. Okay. This little algorithm that we just did actually works. It gives you the best way. But then we went into a discussion. And we talked about counterexamples. And we mentioned this example. We said, what if the first one's 1, 6, and the next 2 are 2, 3, 4, 5, and 6, 7? Well, we can definitely get 3 activities, 2, 3, 4, 5, 6, 7. But if we do our algorithm, we'll think that you can only get what? I think 1, right? Oh, it depends if 6 overlaps. Todd said the book says that 6 and 6 don't overlap, but I usually... half open and... Yeah, I say that these are not okay, because you don't have enough time to clear out the room and get the next one in. It's just the definition, yeah.
The ones you have here under the word greedy, they're organized by end time, and the ones you wrote over there are organized by start time. As your first one.
I don't know what you're talking about. Donna said that these are organized by finishing time, and these are organized by start time. So that's a good point. Smarty pants. Right. This works over here for a particular reason, and it doesn't work here. But let's say we didn't notice this, because I don't think anybody noticed this yesterday, or nobody mentioned it at least. We went over here, we did this counterexample, and then I said, oh, well, let's just change the rules. You know, maybe it's okay as long as we get the most hours, and it doesn't have to be the most things. And everybody goes, all right, I'll buy that. Maybe that's okay. Maybe it's just the number of slots. And then you thought about it for another minute, and you said, wait a minute, that's not good, right? You can still just make this. I'll make this 7, I'll make this 6, and I'll go to 19. Right? So that's 2, 3, 4, 5, 6, 19. This is a longer time sequence than 1, 7 also. But if you do your algorithm, it just starts at 1, goes to 7, and you're done. That's no good. So the greedy algorithm I just described doesn't work if you just have the time intervals coming in some random order. It does work if what Donna says is true. If you order your time intervals by their finishing times, then this algorithm works. You have to notice this. And if you'd play with this, if I threw it out to you as a problem before telling you how to do it, and you spent a whole day thinking about it, you'd probably come up with this. How do you convince yourselves that it really works? Well, think about it for a while and you prove it. I mean, the proof is kind of interesting. It's not that difficult. It's a proof by induction. But basically, the idea is that there's kind of a choice you can make in a greedy algorithm that doesn't hurt you. The thing about a greedy algorithm that makes it work is that it doesn't hurt to make these choices. There might be other answers that are just as good, but if you choose it in this way, you're never going to get worse than the best answer. And that's usually the style of the proof. Usually you say, it doesn't hurt to start with the first one. And it doesn't hurt to pick it in this way. With a minimum spanning tree, there's lots of different minimum spanning trees sometimes for the same one. There's lots of different edges that might add up the same weight. And there's different ways to get them. So we have to prove that if we actually construct it in a particular way, we'll never get anything worse than the minimum one. And it's the same thing here. Greedy strategies just afford flexibility. There's a lot of slack in the problem. This doesn't happen with NP-complete problems. Those are problems that you have no slack in. The best you can do is try everything. If you try to say, oh, well, it doesn't hurt, without any loss of generality, I can do this. That almost never happens in an NP-complete problem. There is no without any loss of generality. In an NP-complete problem, you almost always have to check every single case. That's usually the best you can do. And you can't skip any steps. OK, I'm going to leave the proof and the code for the text and not go over this anymore, but let me just stop for questions. See if everybody has it. Yeah?
If you have two activities with the same end time, do you then need to sort them by start time? Like if you had a 0, 4, that would probably need to be before the 1, 4.
What do you think? Sharon asked the question, what if I had two of the same finishing times? Do I need to sort them by start time, or can I just put them in some random order?
Depends on what your goals are.
The goal is to get the maximum number of...
Are you only doing one time, or are you trying to use them all?
We're trying to get the maximum number of jobs to finish. It doesn't matter how long they are.
But so we're only scheduling for 1 day.
Scheduling for 1 day, right.
Okay, then it does.
So you think it doesn't matter?
It does if you're scheduling only for 1 day. If you're scheduling them all, then probably.
It just means you can get one versus the other, which if you're just looking for the number.
So what if I had 8 of these? I mean, what if I had, 1, 4, 0, 4, 2, 4, 3, 4?
You're not scheduling the maximum number of activities. We talked about this yesterday, but the time.
No, we are scheduling the maximum number of activities. Yes. The time thing was a red herring to try to see if we could maybe fix this. But no, we don't care about how much time total. We care about the actual number of jobs that get done, the variety of activities. So what do you think? I want you guys to answer Sharon's question. You don't think it matters? Answer your own question. Right. It doesn't matter. Right. It doesn't hurt to do it, but the key thing is the overlapping, and the overlapping gets done right by ordering by finishing time. So in fact, it doesn't matter. Right. Good. That's a good question. Good thing to wonder about. Other questions? All right. So what I want to do now is hit the last of the greedy algorithms that we'll do, and it is, I think, either the most or one of the most practical algorithms you'll see. Huffman encoding. Greedy. I mentioned to you there's this theory behind a lot of the greedy algorithms that finds a thread in common with many of them, this theory called matroid theory. Unfortunately, matroid theory doesn't thread in Huffman encoding as a special case. So this really sits off on its own, not part of any more general theory, and it would be nice if computer scientists could come up with kind of a general theory that would be able to lend us the techniques of Huffman encoding to other problems, for us to be able to notice whether other problems had a similar structure to this problem. But it kind of sits off on its own as a little bit of an enigma, kind of a cool problem, extremely practical, just happens to work with a greedy strategy. Who knows what might be similar to it? Oh, before I move on, it reminds me, speaking of similar problems, I mentioned yesterday, I just want to remind everybody, there's a similar problem to this activity selection problem where you're given also these time intervals, but instead of trying to schedule the maximum number of jobs, you want to schedule all the time, all the jobs, but they overlap a lot, and you have to figure out how many different places do you need to schedule them. Okay, so if I have 1, 3, and 2, 5, and 4, 6, how many different places do I need to schedule all these jobs? These two can't run at the same time, right? Because they have to use the same room for one of the hours. So they need 2 separate rooms, and this one can reuse one of the rooms. So we need 2 different places, right? This problem, a minor variation on the activity selection problem, can be modeled with a graph. Every interval becomes a node on the graph. And if there's an overlap, you draw an edge. There's an overlap here. There's no overlap here with either of the other two. This is... does it? Oh, yeah, you're right. Good, good, good. Okay, so this is all of the overlaps, right? Yes, 4 is between 2 and 5. Duh. This graph is called the interval graph of this set of intervals. You saw interval graphs in one problem set. I threw it in there as just an example of how to do breadth first search or depth first search, because they are interesting graphs and they do come up in problems. So here's an example of an interval graph representing these intervals. Every interval is a node, edges between intervals that overlap. But here, a problem on this graph is very, very meaningful. We want to know how many colors do we need to color this graph. So we can do it with 2 colors, A and B, such that no 2 nodes that are adjacent share the same color. This represents scheduling these 2 activities in room A and scheduling this activity in room B. So the minimum number of rooms that you need to schedule these activities is equivalent to the minimum number of colors you need to color the interval graph of the intervals. Okay? This minimum coloring problem is NP complete. But there's a greedy algorithm for this problem on interval graphs. So that implies that the minimum coloring problem might be somewhat doable for this special case of interval graphs. And that's a lot of what we do when we talk about NP complete stuff, is trying to narrow down the frontier between when the problem gets hard and when the problem gets easy.
What's the specialness of the case of interval graphs over the general case?
What makes them so easy?
For the coloring problem, yeah.
It's a good question. That's a good question. I don't think you're supposed to see it at a glance. I can just give you some intuition, is that it somehow resembles this activity selection we just talked about, where the greedy thing worked. So there's that. But outside of that, we can talk about this maybe, in a later day and go through the details and see why it works. And I haven't said that this greedy algorithm is actually going to be polynomial time. It may be, it may not. I just implied that there is such an algorithm, and in fact, this is a problem in the text, in one of the problem sets. And it says, come up with an algorithm kind of like activity selection. So we can talk about whether we think it really is easier or not easier, and talk about what makes things easier. But let me give you a sense. Chris asked, what makes this easier? It isn't always obvious. Another problem, which is NP complete. I draw a big graph on the board, and I ask you to cut it into 2 pieces. Nodes on one side, nodes on the other side. The line can cut any way you want. Just chop it into 2 sets, this set and this set. And I want you to go through the maximum number of edges when you do it. I want the edges that connect those 2 sets to be the maximum possible. Okay? So the brute force is to consider all possible ways of splitting the graph into 2 sets. Right? There's a lot of different ways to do that. Right? How many different ways are there? It's basically how many subsets of this do you have? You put the subsets on one side and put the complement on the other side. So that's 2 to the n different subsets. It's a lot. That's a bad way to do it. And that's an NP complete problem. There's no better way than anybody knows. But if the graph is planar, if I can draw it on the board without crossing edges, then you can do it in polynomial time. And to give you a sense, you think, oh, that makes sense because at least you can see the edges. They don't cross out. But you know what makes that thing work? What makes that thing work, that some of you went through the recitation yesterday, you talked about the maximum flow problem. It works because it uses a variation of the maximum flow algorithm that happens not to blow up in the case of this. It basically converts the graph into something else that you can do a max flow problem on. It's not at all what you would think makes it easy. So I just wanted to mention that because these questions come up a lot and they're the right questions to ask. Okay. Huffman encoding is a way of compressing your files. And it's a really, really good way. Your files typically can get cut down anywhere from 50 to even 90% in their size. So let's say you have some text file. And let's say, just to make it easy for now, all it has is the characters A, B, C, D, and E. Okay, a subset of the ASCII values. And let's say I'm representing these with 3 bits each. So this would be 000, 001, 010, 011, 100. So they all get 3 bits each. And it turns out that in the text, there's a lot more E's than there are anything else. Say it's 90% E's and only 10% all the other letters. All right? So let's say you have 100 characters in your file. If you encode it this way, you're going to have 3 bits per character. You'll have 300 bits in your file. Right? But let's say 90% of those 100, 90 of them are E's. It'd be a lot better to let these guys be a little bit longer and this one a little bit shorter. And then even though the worst case would be that we get all the A, B's, and C, D's and we'd have 400 characters, but that doesn't happen because there's only 10% of these. So say we got this down to 1 symbol and these up to 4 symbols. Then 10% would have 4 characters. That would be 40. And 90 would have 1 character. That'd be 90. 40 and 90 is 130. That's a lot less than 300. That's where the idea of the compression comes from. Look at the characters that appear more often and don't encode them with the same length that you encode all the other characters that don't appear as often. Try to make the length of your encoding be inversely proportional to the frequency that that character occurs. It's very logical. You should think of it the first time somebody teaches you ASCII code, you should wonder, well, why do I want 8 bits for the Q and 8 bits for the E? Why don't I make ASCII code have, very, very few bits for the E and a lot of bits for the Q? And the reason is, there's a lot of reasons. It's because you want to transmit things 8 at a time. I mean, it would be crazy to do that in general. But it's not crazy to go ahead and make your compression and then just send it over as binary and then decode it on the other end. So that's what we're going to do. We need a way to re-encode these numbers away from the ASCII way down to different size values and then put it back to ASCII when it gets there on the other end. So we've got to encode it and decode it. And in between, the file gets incredibly compressed. Okay, that's the idea. Are there questions about the idea?
How do you know when one character ends and the next one starts if they're of different lengths? If you didn't know that they're all length 3, you know they're all length 3, so you chop them up 3 at a time. But one of them is 1.
All right, so Sean asked an excellent question. He said, if I'm going to make these different lengths, then basically how do I know how to decode it at the other end? If they're all like in ASCII, they're all 7 bits long or 8 bits long, then every 8 bits, I chop them off, I send them to my decoder, I got a character. It's easy. But if they're different lengths, what do? How do I know to stop after 3 or after 1 or after 4?
Just guess E 90% of them.
That's a nice solution. It's a really good question. It's a really important question because if it was a real problem, then Huffman encoding doesn't work. And it turns out that it's not a problem. And it's one of the key things that turns up from Huffman encoding. So let me put some Huffman codes down here, and you'll tell me whether it's a problem or not. What if I make E be a 1, and I make this be a 1, 0, and I'll make this be a 0, 0, and this will be a 0, 1, and this will be a 1, 1. What if I do this? This is not a Huffman encoding. This is a goofball encoding. And it pinpoints Sham's question precisely. Okay, now you get this particular message that comes. What characters does this message represent? It's ambiguous, right? Here's one set of characters it could be. This one is an E. This D is a D. These 2 1s are a D. And then the 1 0 is an A. That's one thing. Ida. Or what else could it be? It could be D, D. Oh, that's no good. Can't be that. What else could it be? Can it be anything else? It could be D, E, A. It could be Dia.
It could be D-D-D-A. It could be E-E-E-A.
It could be E, E. It could be 4 E's. It could be 3 E's and an A. Good. Even 2 choices is death, right? I mean, we don't need to get them all. This is bad. This is exactly Sham's question. So the answer to your question is that the Huffman encoding will come up with a set of codes that this never happens for. Doesn't matter that they're different length, but we will never have an ambiguity. We will be able to parse it, same word as we use for context-free languages, we'll be able to parse it going left to right in linear time, even in real time, even in online time. Feed it into me a character at a time, I'll be able to know exactly when the next character is finished.
Without a spacer.
Without anything. Right.
Just reserve the first bit.
No, nothing like that. It's automatic.
Codes don't overlap.
Okay, so
Right. That's
good. You're all getting the right idea. Use a tree, yes. Right, good. Use a tree, get codes that don't overlap. There's a particular notion here that has a very specific definition. A set of codes is called prefix-free if no code is a prefix of another code. If no code appears as the first part of a string of another code. In this, is this a prefix-free? No, because E is a prefix of D. And that was really our whole problem. What if I switched it? How can I make this a prefix-free code? Can I do it? Let's come up with any prefix-free code.
Make E3 zeros, and then E3.
Is that prefix-free? Well, then I got to change B to 001. And what do I make E? I can make E11.
You can make E1 and make A.
This is a prefix-free code. Not that it's a particularly good code or the best code, but it's a prefix-free code. You can check with every pair that none is a prefix of the other. No string starts with another string. If this is the case, then whatever encoded string you get, you'll be able to decode it unambiguously, regardless of the length. And why is that? Because since no string is a prefix of another one, you just look to see when you get a match. And when you do, you know it's got to be that one. And you strip it away. So I'll write down a particular one here. Let's decode this. 0, 0, 0. What does that have to be? You didn't get any match for a 0. You don't get any match for a double 0. You finally get a match for triple 0. That's D. You continue. 0, 1, match C. It's just automatic. 1, 1 has to be E, and 1, 0 has to be A. If you have a set of prefix-free codes, the parsing or the decoding is automatic. Okay? So it's a good question, and that's a good answer. Now we just have to make sure that the Huffman encoding gives you this prefix-free stuff, and in fact, it gives us the best one, the one that's going to minimize the total number of bits in the file. Probabilistically, we're assuming in general that the percentages are true. Yeah?
Does it work with all languages or just English?
Anything. As long as you have the frequency table. As long as you can tell me how often does this character occur relative to this character, it works with any language.
Shouldn't you actually count them in the file that you're dealing with?
Yes. Yes, you can.
You don't have to rely on.
Right. You can certainly do what Chris said. You can certainly take the file you want to compress, actually count the characters, and then make your encoding based on that counting. Absolutely. Absolutely you can.
Is this used?
Yes. Yeah. Yes, it is used. And it's amazing how much it compresses a file. You can, I mean, a cool problem set, and I didn't give it because you can only have so many problems, but a cool one is just to implement this and then just filter through all your files on your Unix system and decode it back. And there it is, exactly pristine the way it started, but in between, when it goes to the encoded state, it gets cut down, by 75%. And it's especially useful, when you're transferring things and you want to cut the size down.
this, or are they all based on this? or-
MP3s after they do all the psychoacoustic analysis, do a Huffman step afterwards to compress it down further.
It's usually the last thing that gets done. It's usually the thing that gets done when you have just the final thing ready to send. But there's all sorts of other compressions that get done on different levels. Like the difference between a GIF and a JPEG has nothing to do with Huffman encoding. It has to do with how much information do we really need to send to have the picture look the same. So a JPEG does it fit better, right? A GIF has more information than our eyes really need. Same thing with sounds. But that stuff generally comes before you do the Huffman encoding. Okay, so let's see an example. This example, again, I'll do one example, a couple examples that aren't in the text, one example that is. The example I'm doing now is in the text. So here's the details. Again, just to make the example seeable on a board, we'll just use 6 different characters. And here are the frequencies. 45, 13, 12, 16, 9, 5. These are meant to be percentages. They could be raw numbers, but this is a percentage. There's 100 characters altogether. All right. We're going to do this just like you would think. Pretend that you weren't a genius and you didn't see the theorem and you didn't know it worked. What would you try? You try to make the things that had the most frequency have the shortest encoding, and the ones that had the smallest frequency to have the longer encodings. So what we're going to do is just what Jeff said a minute ago. We're going to build a tree. We're going to build the tree from the bottom up. When we're all done, it's going to look like this, something like this. A, B, C, D, E, F. At the end, it's going to look something like this in the sense that the leaves represent the characters that you're trying to encode, and a path from the root to a leaf tells you the encoding. In particular, we'll assume that zeros go to the left and 1 goes to the right. So the encoding for an A in this particular tree would be 0, 0, 0, 0. The encoding for B would be 0, 0, 0, 1. The encoding for C is 0, 0, 1. The encoding for D is 0, 1, etc. Why do we do it this way? Because this way, we're guaranteed to have prefix-free codes. No path from the root to a leaf can be the same as any other one because it branches off before it goes to the leaf. So you can't have a complete path here being the prefix of anything else. In other words, we don't have the letters appearing in the internal nodes. We split them all at the bottom. If that's the case, there's no prefix issues. That's why we do it this way. Yeah.
But A now has the longest.
This is a very bad one. You're right, Joe. I just wanted to put an example up so you'd see the structure of where we're going. This is not the one we'll end up with. This is a bad one because A has this long one and we want A to have a short one. But it'll give us some motivation. What we want to do is build this tree from the bottom up. And what are the ones we want to build up at first? We want to build the ones that have, we don't want A to be included. We want A to be like one of the last ones, the ones that end up here. So we're going to start connecting things that have the smallest frequencies. So they end up at the bottom with the longer paths. Let's do it. Any questions before we get started? All right. The 2 smallest ones now are 9 and 5. So we take them together and we make, I'll do down here, we make a little tree, 9 and 5. And I'll call it E and F. Those are leaves. And for our own benefit, we add these 2 together because the collective frequency of these 2, E and F, together is 14. Everybody else is still, these 2 are taken care of, but everybody else is still on its own. A, B, C, D are lonely. You continue this process in a greedy way. Take the next 2, now it's not just letters, but collections or subtrees that are the smallest frequencies. 12 is 1, and 13. Okay, 14 is bigger, so we leave this where it is. Now we connect 12 and 13. It looks like this. BC, 12 and 13, and that gets labeled 25. So now we have 4 possibilities: 14, 25, 16, and 45. What are the 2 smallest? 14 and 16. So we merge those together. Oh, we have to be... I want to be consistent and put the bigger one on one side and the smaller one on the other side. That's important. It's important to choose. It doesn't matter whether you choose 0 or 1, but the bigger one should always be on the 0 side and the smaller one should be on the 1 side, or vice versa, and not to switch that. So now we're going to take 16, which is D, and connect it up with 14. Now I'm ready. And this is labeled 30, and I check that off. Now I'm left with 3 subtrees: the single node, 45, and these 2, 25 and 30. So I take the 2 smallest, 25 and 30. 30's on the left, that's good. 0 here, 1 here, and this is labeled 55. Now there's only 2 left, the single node 45 and this big tree 55. And I can put those together like this. The top of the tree is labeled with the sum of all the values, 100% in this case. And this is the actual Huffman encoding. So as you can see, Joe, so the A does end up with this teeny little weenie path, and these E and Fs end up equally at the bottom. When you discover this algorithm, where you start playing with it, you got to get a gut instinct that you got lucky here. It just feels like you're not going to be able to do better. It doesn't seem like there's any place we might have been able to improve this. And that's kind of the intuition behind every greedy proof. Not that this is definitely the best Huffman tree, but that you're not going to get a better one. Now I know those two sound the same, but it's the intuition involved in it. It's that there's slack in this problem, that as long as you do this, you definitely can't do any better. Okay, questions about this? No. No questions. Yes?
Is there, we talked a little bit back in December about information theory, you know, how much information there is in something. Is this sort of begin to get fundamentally to the level of where you can't make it smaller because there's just that much?
You mean, can you prove that compressing further is impossible because of information theory kind of issues? I don't know. I don't know.
Compression gets better than this, but not much better. I mean, you know.
Right.
So.
Right. My guess is that I mean, information lower bounds are more kind of, information theory lower bounds are more like the universe doesn't allow you to do any better. And my guess is that this isn't close to that. But I don't really know. It's a really good question. I can ask. I mean, I have a colleague who's an expert in information theory, teaches it every single year and knows a lot about it. He'll tell me in a second, and I'll let you know. Yeah.
Well, the efficiency of the algorithm is totally based, in this case, on that we have 8-bit characters. Right? So it's about the chunkification of the original data set. A gzip works differently in that it takes variable length data sets up to 32K, and it does analysis on them individually. And it could be more efficient if it took 1 megabyte data sets, but there's a speed trade-off there. So
right. So
if you took an infinitely long data set and did an infinitely sophisticated input,
you could do better. Right. I don't. Right. I'm not sure what the absolute best is, and what the amounts are provably, you could say, about, you know, the best compression. I'm not sure. There's one more point I want to make before we let this go. I'm going to write down a string here. Just came out of my head. Let's see, there's a point to this. Let's see if we can parse this string. Let's say that this is an encoded version of some letters. What are the letters? 0, 0, 1, 1, F, 0, oh, 1 is A, 0, 1, 0, 1, 1 is C, 1, 0, 1, 1. So it's okay, right? Fakaka, right. So here's the real question. Is it possible, what if this got corrupted along the way? Is it possible that you could get a message that has no decoding, that would crack your program up? Not that you get a wrong decoding. That's clearly you could do that. I could just switch these numbers to give you a different word. But is it possible that if one of these zeros and ones got corrupted, your algorithm would say, there's no match, and bomb? Sure. Give me an example. That's my question.
Two zeros at the end. Yeah. How about 0?
How about 0?
Let me just go further looking for some of that.
All right, so Sham thinks maybe that's just a special case. Can you give me a longer one where it cracks out?
Anything that's not in the full binary tree, right?
No, that works.
You can get D.
That's D.
D, nothing.
So add a single
The
zero.
last character.
You can always add,
Right.
you can always get to a point where you get stuck and can't continue. And that's important to realize, and I'll just make this one little reference to discrete math for just a second. This Huffman encoding is a function. It takes letters and turns them into binary numbers. Okay? You throw in a letter, you get a binary number. Is the function, so it goes to binary numbers of this length. So if you have a bunch of letters, it gives you a long binary number. If you have a single letter, it gives you, so it defines a function on a string of characters, turning them into binary numbers. The Huffman encoding takes a string of characters, turns it into a long binary number. Question 1, is the function onto? Does it hit every binary number? And the answer is no. It doesn't hit this one. Okay, so it's not an onto function. That didn't seem to bother us. Is it a 1-1 function? Is it possible to have two things? Here's what 1-1 means. Is it possible to have two things that get encoded into the same binary string? No. Right, you couldn't decode it if that was the case. So mathematically, Huffman encoding needs to obey the rule that the function is 1-1, but not necessarily onto. Right? So that's why you have all those terms. It's because this is really a special case of something that we understood before in a more general way. But it comes up here. You should realize that it came up here even though it was hidden. That's all. Questions about this example? We're gonna do one more before we quit. Yeah.
Is the end result that as long as you keep adding characters to the end, you can always keep decoding? That you can only get stuck when you...
Oh, so Michael's asking, can you only get stuck at the end? Can you get stuck in the middle?
No, I don't think so.
What if you don't get to your What about 0, 1?
Well, things that begin with a 1 after...
No, but there'd have to be a 0 or a 1.
Things that begin with a 1 after a character, after a recognized character. Oh no, then A.
It seems like you can always match up until you get a prefix which doesn't actually exist as one of the leaves.
What happens if somehow your data gets corrupted and you miss part of the string coming in? Is all of it going to be offset from then on?
You're dead, yeah. Yeah, I think you're dead then. there's a whole other thing that we won't talk about error detection and error correction that make sure that doesn't happen. You basically add extra bits to make sure that if errors occur, you can detect whether the error occurred and correct the error, including errors in the bits you added to do the error correction. And it's a really cool topic. It's very interesting, but it's not for today. And it's kind of computer science-ish, but it's really a mathematical topic per se, and it's a good topic. It actually relates, ironically, it relates to a puzzle Sam Klein told me right at the beginning of ADU, which made me waste 3 days thinking about it instead of working on your lectures. The puzzle goes like this. You know that if I have a secret number in my head and I'll answer yes or no to your questions, that you guys can guess it in log n steps using binary search. Right? You pick halfway and you can ask yes, no questions. So his question to me was, what if we play the same game and the person who's giving the answers is allowed to lie once? I'm allowed to tell you the wrong answer one time in the whole sequence of the game. Then what's the best strategy? What's the minimum number of moves that it takes? So it turns out, after I thought about this for 3 days, I finally realized that it's completely equivalent to the idea of error detection. You basically want to add on a number of questions so that if there's a wrong bit in the answers to those questions, you can figure out where it is. And you have to add on that many extra questions, enough to be able to detect and correct that bit. So it's equivalent to this stuff. So after 3 days, I went back to him and I said, how interesting. You know, because this is something he solved, I don't know, 20, 30 years ago. I go, I didn't realize it was connected to error correction and detection for 2 days. And then I finally noticed the connection. He goes, what's that? Error correction, detection? So he had never heard of that and knew nothing about it. And he had just solved this on his own in some ad hoc way without using any of the built-up heavy machinery that comes with error correction and detection that I was finally able to leverage once I noticed the connection. It's kind of interesting. I want to do one more example of this. Ready? Last example. There's a question somewhere in some text, might be in yours, and it goes like this. It says, hey, what if you get a bunch of characters and their frequencies are the Fibonacci numbers? What kind of a twisted person would give you that question, right? 1, 1, 2, 3, 5, 8, 13, 21. Say those were the frequencies. What kind of Huffman encoding do you get? And then generalize it. Tell me in general. So it's actually not such a hard problem. It's kind of a cute problem. But it's interesting to look at because it does give you another insight into the structure of Fibonacci numbers. Let's do it and see what kind of encoding we get. We'll just label them by the numbers. We don't need A, B's, and C's, and D's. So what happens first? You join the two ones. Then what? Then the two, right. 2 gets joined here. Yeah, what the hell? 4. And what happens next? Join that with a 3.
Looks like a ladder.
Looks like a ladder, right. Join this with an 8. What happens with Fibonacci numbers is that, and you'll notice, you actually will discover an interesting identity about them. What do you notice that's happening here? You add the previous 2 Fibonacci numbers all the way up, and they get to be 1 less or 1 more than the next one, right?
I forgot 5.
Is that what happened?
Yeah.
Oh, I forgot 5. Something's fishy.
8. You want 5.
That's what it should be. What happens is, as you add up, you get something that's 1 number smaller than this. And you wonder, is that always true? And if it is true, then you're going to get this ladder structure that Joe noticed. And it is really true. And you can prove that. And actually, you did prove it. You just don't remember because it's such a haze from 3 months ago. What is it exactly that we're proving? What does this 12 come from? comes from 5 plus 7. Where'd the 7 come from? 3 plus 4. Where'd the 4 come from? 2 plus 2. Where'd the 2 come from? 1 plus 1. This 12 here is 1 plus 1 plus 2 plus 3 plus 5.
It says one the other Fibonacci.
Say that again?
The other Fibonacci?
The one that starts with just 1.
You mean Sylvia Fibonacci? Which other Fibonacci?
The one that starts 0, 1. I don't know.
You mean the one that starts with 1 further up? Oh, I see what you're saying. Right. That's one way to look at it. I was thinking of it, if you add up all the Fibonacci numbers up to a certain point, it will give you 1 less than the Fibonacci number 2 over. And you can write that down. The sum of all the Fibonacci numbers from 1 to n minus 2 equals fn minus 1. And you prove something just like that. And there's variations of this. There's a lot of things you can prove like this. Anyway, so you get this Huffman encoding that looks like that.
If you just rank them according to their frequency and do the coding, you get a different code.
Oh, like you just make them 1 and 2 and 3 and 4 and 5? Yes, I think you would get a different one. Yeah, I think you would, because this sum is important. So if you just ranked them and you made them kind of linear, you wouldn't get that quantitative distinction that you would with the actual frequencies. And I bet I could come up with a counterexample quickly, but I'm not so sure I'll get it right the first try. But I'm pretty sure a counterexample would come up very fast if you just ranked them.
The counterexample to what?
That I would use the Huffman encoding on a ranking structure instead of the frequency, and I would get a tree that's different than this. Yeah.
Would the codes be like one better than the other? Is it?
This one's always the best.
It is.
Yes, you can prove that this is the best, that you can't do better than this. So whatever we get different would be not as good, or at most as good. But I'm sure I could come up with one that would be worse. An example that'd be worse.
This one would be worse. I mean,
This one would be worse right away, yeah? These would be 1, 2, 3.
you get joined in somewhere far down the tree, and you'd have a kind of a pretty balanced.
Oh, you mean this one would be worse?
No, that
This one.
Yeah, you'd have a pretty balanced tree, and A would be 2 or 3D.
Oh yeah, A would come in earlier because the 45 wouldn't keep it from being connected later. It would get added in because it's only 8. Yeah, that's a good point.
Right, the total length, like the longer it is, you end up with some things that are a lot of bits.
Yeah, I think Chris is asking whether the bushiness of this tree relates to how much compression you get, or something like that. I mean, can you look at the picture and get a sense of whether you did well here or not well? Well, let me ask you this. If the tree looks like this, it's a completely balanced tree. Do you think you did well or not well as far as compression goes?
No.
Not well, right? You kept everything the exact same length. You're probably getting no compression.
The less the spread is between the what we're trying to encode, the bushier it's going to be, and so the less the spread.
Right, so what about something like this? Something like this is going to give you good compression, because what's bad is the fact that you were using equal size encodings for something which was so exponentially off in its frequency. So the more the frequency is off, I think the better compression you'll get, for the most part. Or the longer and thinner your tree is, the better compression you'll get. Other questions? Okay. Super. Super. Okay, new topic. New topic.
We'd like to have a little bigger if we have.
That is italics. All right.
Now we can read it on the 20 kilobyte per second.
Oh yeah, that's pixelating. This is an important topic, and I want to take today as a good day to get us started without too much pain, and then going into more details once you've kind of had a good introduction. So here's where we start. No pain. No pain. By the end of today, I want you to know what NP really means and what NP complete really means. And then you'll have it'll start to make sense once you start seeing lots of examples. But you got to get at least the terminology down, and I'll try to throw in as many specifics as I can as I give you this terminology. So, here's the first thing. We did a bunch of different algorithms this year, different problems. Somebody gives you a graph, you want to know what the minimum spanning tree is. Somebody gives you a bunch of points, you want to know what the convex hull is. Every one of these problems, somebody gives you a bunch of numbers, you want to be able to check if they're in order. You want to check if this one's the biggest one. I'm saying these in a very particular way. I'm talking about these problems in the sense of somebody gives you something and you answer yes or no. Some of our problems weren't always that way. Like in sorting, you actually move things around and you sort them. But in talking about problems, when we talk about NP-complete problems, we simplify every problem so that it turns into a yes or no question. And all your program ever does is compute for a long time and say yes or no. Now, you must be thinking, well, doesn't that rule out some kinds of problems? And it does rule out some kinds of problems, but it turns out that if your computer is able to answer the yes or no version of any problem that I've converted to a yes or no, it can usually go ahead and do all the other details within a polynomial time factor extra. For example, sorting. How do you turn sorting into a yes or no question? I give you a bunch of numbers and I ask you, yes or no, are they sorted? How long does it take you to do that? Linear time. You have to go through the list. If I actually asked you, if they weren't sorted, to actually sort them, it'd take a little more time, right? It would take n log n. NP-complete is supposed to distinguish between something that's polynomial and not polynomial. So the fact that we have lost the ability to talk about a problem that takes n log n, and instead we're talking about a version that takes n, doesn't really hurt us. Within a polynomial time factor, we're still able to distinguish that problem from problems that can't be done in polynomial time. So we're talking about a simpler collection of problems, problems that can be done by answering the questions yes or no. Okay? And without any loss of generality, it won't hurt us. We're not going to lose the ability to talk about any particular problem. So what about a problem like shortest path? How do you describe that with a yes or no?
The same thing. Use this set of points.
Okay, so what you do is you do something like this. You say, here's the graph. Here's the start node. Here's the finish node. That's all part of your input. And you want the shortest path from here to there. So what you do with a minimum problem like that is you add in one more parameter. You throw in a number like 35, and you change the question to, can you show me a path from here to here that takes 35 or less? Okay, if you can answer that question yes or no, then you can also find the shortest path question. How do you do it? You can just start with 1, move up to 2, move up to 3, move up to 4, and keep asking your program to say yes or no. And it'll keep saying yes, or it'll keep saying no, and at some point it'll say yes. I can't do it with distance 1. I can't do it with 2. I can't do it with 3. No, no, no. Can you do it with 35? No. Can you do it with 36? Yes. So I say the shortest path is 36. I can figure out minimums as long as I have yes or no ability, just by running through my algorithm so many times.
Wasn't that a completely different problem in the coloring case that had different, one where you say is it or is it not less than?
Right, so let's consider the coloring example. Say I have a graph. It's a good question about coloring. Coloring is a perfect example. Here's a graph. I want to know how many colors I need to color it with a minimum number of colors. How do I describe that as a yes or no question? I give you the graph. I give you a number like 10, and I ask you, can you color this with 10 or less? The input is a graph and a number. The question is, can I color it with that number of colors or less, yes or no? A more specific, easier question than that is, I give you a graph. I don't give you a number as a parameter, but I just ask the question, can I do it with 3 colors or not? So that's fixing the number.
What was the other thing?
The other thing is that the number is a parameter. One is that the number is fixed, and one is that the number is a parameter. Maybe the parameter is what makes it hard. Maybe it's the fact that that I'm throwing in that number that makes the problem hard. But if I fix it, it might be easy. For example, we talked about the bandwidth problem yesterday. If I give you a graph and I give you the question, does it have bandwidth 2? You can answer that question in order n squared time. But if I give you a graph and I give you an arbitrary number and I say, can you get bandwidth less than this? There's no polynomial time algorithm to do that. If I give you the number 10, it's going to take n to the 10th. If I give you the number 30, it'll take n to the 30th. If I give you the number 40, it'll take n to the 40th. And if the that's not polynomial in general, because that k could get as large as you want. It could turn into n. And then it ends up n to the n. And that's not polynomial, n to the n. So the first thing you have to do is get used to thinking of problems as yes, no. And every problem we're going to write is going to be written as a yes, no. It makes things easier, and it gives us a chance to deal with problems that otherwise would be too many different kinds. So that's the first thing. Those kind of problems are sometimes called decision problems, because you're deciding yes or no based on some input. Some problems are naturally decision problems. I give you a graph. Is there a Hamiltonian circuit on the graph? That means, is there a way to get through all the nodes and get back to where you started without backtracking? Yes or no? Simple problem. You don't have to fix it because of a minimum or maximum. That problem is NP complete. If I give you a graph and I say, is there an Euler circuit? That's a path that goes through all the edges exactly once. Not the nodes. It can go through the nodes more than once, but it goes through the edges exactly once. The answer to that question can be done in linear time. You just check the degrees of all the vertices. Okay, and if you have an even number of even degrees, you're all set. So some problems are easy and some are hard. The very first day of this class, I made a whole list of problems. This one looks like this one, but this one's hard and this one's easy. And we tried to get a sense of just how confusing it was to figure out whether a problem was easy or hard. So we're going to get back to that now, and we're going to try to do it a little more formally. So the first thing is that every problem is a decision problem. The next thing is that some of those problems can be solved in polynomial time. That means n to the some number, fixed number. It's got to be a fixed number. It's got to be n cubed, n to the 4th, n to the 5th. It can't depend on the parameters to the problem. It can't be n to the n over 4. It can't be n to the k if k is a parameter in the problem. Okay, you can't have any parameter showing up in the exponent. That won't be polynomial. You have to have, to show it's a polynomial time algorithm, it's got to be n to a fixed number. Here's a little picture. The set of all problems that have polynomial time algorithms are in this group called P. And everyone will have a different point in the universe. So this is shortest path. And here's minimum spanning tree. And here's the maximum problem. Get the maximum of a bunch of integers. And here's the max flow graph problem. And here's convex hull. Every single problem that can be solved in polynomial time is in a constellation somewhere in this big circle. And there's a circle out here called NP. No, it doesn't mean not P. It almost seems like it does because it's not P. And the things in it are generally not polynomial, but it doesn't mean not polynomial. It stands for the words non-deterministic polynomial. This is deterministic polynomial, and this is non-deterministic polynomial. Non-deterministic has a very specific meaning in theory of computation. That's what I was telling you before. I don't want to get too much into the gory definition of it. I will give you some intuition, and I'll give you an equivalent definition that you can deal with without getting too hairy into the details. But for now, it stands for non-deterministic polynomial. And I'll tell you what that means right now. Non-deterministic. A deterministic polynomial time algorithm is just the ones you know. Deterministic. You run your program. You can determine what happens at every step along the way. It is determined. You run it with a given input, and you can watch what happens step by step by step. Non-deterministic is a strange kind of program. It's a program that you actually do not know what it's going to do at every step. At every step there might be choices. And any one of those choices could be taken. And if any one of those choices gives you the right answer, then your program solves the problem. And if you're thinking, well, how do we do that? The answer is you don't do it. You don't have programs that are non-deterministic. Okay, your programs are deterministic. They go in a straight line. Non-deterministic programs at any point along the way, let's pretend I created a language. At any point along the way, you're allowed to do this. For all these cases, choose one. And if any of them work, then come back and tell me. And it can do them all in parallel. Non-deterministic programs are basically programs intuitively now that can do things in parallel as long as you're connecting the resulting answers with ORs. So if this or this or this or this, all those possibilities can be done at the same time. You can't do it with ands. That's a different kind of parallelism. And non-deterministic has nothing to do with that. It's basically allowing parallel ORs in your program. Now that's the theory of computation, intuitive definition of it. I'm going to give a more rigorous equivalent definition that relates better to algorithms. But from a theory of computation point of view, intuitively what it's doing is letting your programs do parallel things at the same time as long as the results are things that you're ORing together.
That sounds deterministic.
Well, you could do it deterministically, but you'd have to try every possibility and backtrack. And that would take a lot of time. The time that we count for a non-deterministic polynomial time algorithm is, you imagine they're all being done at the same time. Let me give you an example. Yeah.
For each step, there can be these branches that go off.
At any point in your program, you can have branches that go off in parallel, as long as when they return back an answer, you're going to OR those yes or no's back together.
Are they full branches? Like, can those
yes.
branch?
Yes. And that gets, yes, they can branch at every stage, but the truth is, you could actually combine all your branches into one main branch. And we're going to end up defining it by one main branch rather than at every step. Because at every step, you kind of lose the intuition, and with one main branch, you keep the intuition. So let me now talk about a problem, a real-life problem. This is a Boolean formula with nots and ors and ands. Here are the ors, the pluses are ors, and each of these parentheses is like an and. So x or y or z bar, and x or y or u bar, etc. I have a long list, say 300 long. And the problem, famous problem, is how do you figure out whether there's a way to assign true and false values to the x, y's, and the u's and the v's to make this whole formula true? Or more specifically, to get at least one of the variables in each clause to be true. This and this and this and this. How do you do that? Well, give me a brute force method.
Try every true and false.
Try every true-false assignment. List your x, y, z's, and u's and v's on the side, and how many different true-false assignments are there for n variables? There's 2 to the n. So you try every one of those 2 to the n, and for each one, you run through your formula, and you check to make sure that one of the things in each clause evaluates to true. And then if that turns out okay, you come back and you say, yes, I can do it. And if they always evaluate to false, then you come back and you say, I can't do it. How long does it take your algorithm to do this? It takes 2 to the n to generate all the possibilities. And how long does it take to go through this list? Well, I have to tell you how long it is. Let's say it's m clauses long. So it's going to take 2 to the n times 3m, because I got to check each one of these to see if they're true or false. That's an exponential time algorithm. Okay, it's very slow. What do you...
That's just n, right? 2 to the n times n. Is it 3m?
Well, I assume there's 3 in each one.
Well, if you assume there's 3 in each one, then that's just n. What is it?
The n is the number of variables I have. But the variables can appear in numerous different clauses. So n is the number of variables. And m is the number of, I'll call them clauses or conjuncts or things with parentheses around them. That's a slow algorithm. That's the best anybody knows how to do for this problem. Okay, this is an NP-complete problem. This is the first known NP-complete problem. It was proved to be NP-complete in the early 70s by Stephen Cook. Interestingly enough, in parallel, although there wasn't such great communication between the Soviet Union and this country in science, sometimes there's a lag. There's another guy, Levin. God, I hope I got his name right, because he's going to watch this video and go, I did it first also. He did. He in parallel discovered the same idea, but it wasn't this problem he came up with. He came up with a tiling problem, which has to do with a puzzle about whether you can tile things with the certain edges on the tiles, and he proved that that was NP complete. But this is known generally as the first one because his work was more publicized, at least in the West. Actually, Levin now is, I think, at BU, so he's like right down the block. I could even yank him in here and he can talk about it. Yeah.
I seem to remember vaguely from before that you said you proved a problem was NP complete by reducing it to another.
Yes. How do you get the first NP complete problem? Well, let me answer that in a minute, as soon as everybody knows what NP is, because we're not done with NP yet. First we got to get NP, then we can talk about NP complete.
Did they really prove that these were NP complete?
Yes.
They were NP.
No, that they're NP complete.
Completeness already. Okay.
Yes, yes. Otherwise you can't get anywhere. You have to get the first one.
All right.
Right. So both of these people in parallel, I think around 1970, something like around then. This, again, is a deterministic algorithm. It's slow. It's exponential. How would you do this with a non-deterministic machine? Let me describe it, because all these non-deterministic algorithms are magic, because there isn't any such non-deterministic machine. But you go out to your magic store, and you tell the guy the password, and he brings you into the secret back room, because you say you want to buy the non-deterministic machine. And it's very dark and dreary, but if you give him enough money, he hands you the non-deterministic machine, and you can write programs on it. And you write a program that says, for every possible assignment of variables, for all 2 to the n, check whether this formula is satisfiable. If this one, or 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 this one ends up satisfiable, then I say yes. Otherwise, I say no. I combine 2 to the n possibility branches in an OR statement. Okay, check them all in parallel. Instead of checking them one at a time, check them all at once. Okay, don't check them one at a time, check them all at once. How do you really do it with a real machine? You don't. You have to check them one at a time. But this is a non-deterministic machine. So if you give it a whole bunch of things to do at the same time, it will do them at the same time for you, and it will only take time proportional to how long it took you to do one of them. Okay, as long as the answers are ORed together when you come back. And they are. As long as this one or this one or this one works, the answer's okay. Yeah, Sharon.
Why doesn't a machine with parallel processors, why can't it solve that?
It could if you had enough parallel processors. You'd have to add processors every single time you'd have to have 2 to the n processors.
Okay.
And the answer is it could. So yeah, you could build a machine like that. But the idea is that as your size of your problem got bigger, sooner or later you'd run out of the ability to have that many processors. So it only helps up to a point. Good question. How many steps is this non-deterministic algorithm said to take? Just takes 3m. Just the amount of time it takes to check one of them. All the 2 to the n is done in parallel. Every one of them takes 3m. So all that 2 to the n times 3m gets collapsed down to just 3m.
You can't do that all at the same time because it's ANDed. Is that right?
No,
because they all have to have a 1.
Oh, you can't parallelize this anymore because you have to check ands. Right, right. You can't parallelize any more down the line. That's true. This is the best you can do. Yes, good question, Chris. That's a non-deterministic polynomial time algorithm. Polynomial time because this is polynomial. Non-deterministic because you used your magic machine. Almost any problem we've ever talked about all year long can be done with a non-deterministic polynomial time algorithm. You get incredible power. In fact, it's going to be a couple of days before I actually come up with a problem to, maybe next time, but at least a day. I'm going to give you a problem and I'm going to say, well, how do we do this in non-deterministic polynomial time? And even that won't be enough. We'll have to go one step out even further. There are some things that are not even in here. But almost everything you've seen this year, even the hard problems, are all sitting in NP. Yeah, Chris.
So these are problems that if we have a good guess, that we can check in polynomial time.
Right, right. So that's exactly what I'm going to say next. It's very important. The way to get around this sense of the branching, which is the theoretical theory of computation way to do it, is let me give you an equivalent formulation. If you want to just guess a solution to this, pick a true or false assignment. And you can check it in polynomial time, check it in 3M, then that's a non-deterministic polynomial time algorithm. Think of your algorithm as having two steps. One is it gives you a guess of the solution, and the second is it checks that guess. You can make a guess in time n, assigning true or false randomly to each variable, and then check that guess in 3m. So n plus 3n, that's polynomial time. That's equivalent to checking them all in parallel. So just focus on one. If you can do one and check it and guess it, that's enough to imply a non-deterministic algorithm. Because you could clearly just try them all, and if any one of them worked, you'd be okay. So that's why there's an equivalence. So from now on, when we talk about non-deterministic polynomial time algorithms, we'll talk about algorithms that have two stages. One is a stage where we guess the answer, and one is a stage where we check the answer. What we don't have to do is try every possible answer and check each one. We just have to make sure that we can guess one and check that in a short amount of time. So it's a magic machine that if it can guess one and check one, it can do them all at the same time. All right. Are there questions about this so far? You're going to see lots of examples of non-deterministic algorithms, and you'll see examples of problems that can't make it. Before I quit, I also want to say two more things. One is the answer to Erica's question, which is a good question. How do you prove the first problem is NP-complete? Well, I like to answer that, but not everybody remembers what NP-complete means. So you need to know what NP-complete means. A problem is NP-complete, number one, if it's sitting in NP. That's the first thing. It's got to be in here. It's got to be someplace in here. But there's another intuitive part of the definition, at least. And the second part is that every other problem in NP is at least as hard as that problem. Sorry, I said it backwards. That this problem is at least as hard as every other problem in NP. It's harder or equally hard to all the other problems. It represents the hardest problem in the group. To be a little more formal, if you could solve the particular problem that you are calling NP-complete, if you could solve that in polynomial time, if you figured out a way to move this from here to here, then you could also solve all the other problems in this constellation in polynomial time. That's what hardest means. It's the hardest problem if solving it in polynomial time implies a solution to all the other problems in polynomial time. What's an example specifically of doing this? We talked about convex hull and its relation to sorting. Remember that? If you could solve convex hull, you could solve sorting by doing a little pre-parabola processing of the numbers, making them into points, running your convex hull, and then doing sorting. So because of that, which is harder than which? Convex hull is at least as hard as sorting, because if you could do the convex hull problem, then you could do sorting. A problem is NP-complete exactly along those lines. If you can convert any other problem into a version of this problem, so that solving this then would solve all the other problems, then that problem is NP-complete. If you could show that this is in here, then the whole bullseye collapses, and then P equals NP.
It's the NP-complete problems you have to reduce to.
Right.
Not the NP, not all the NP problems.
All the NP problems reduce to the NP-complete problems, every single one of them.
Oh, so there are no NPs.
There are no
that are not
NP.
complete.
There may be, but that doesn't. There may be. So there are lots of problems in NP. So I'll put stars next to the ones that are NP-complete. These are the ones that are at least as hard as all the others.
Right. So if you prove one of those, if you equate one of those with your new problem, then you get all the NP-complete ones. Because they're all...
If you show that your problem is at least as hard as any one of these,
then you get all the stars.
then it's as hard as all of them.
But then do you have to go case by case and get all the non-starred ones?
No, because all the non-starred ones are no harder than the starred ones. The starred ones are the hardest ones. If you take a new problem and show that your problem is at least as hard as a starred problem, then it's certainly harder than all the other.
But that's only if at some point
You need a
To
first
get
one.
the star, you had
Right.
to also not only compare it to one other starred problem, you had to compare
Right.
all the NP
Good,
non-starred problems.
good. How do you get your first starred problem, your first NP complete problem? That was Erica's question. How do you get your first NP complete problem? Once you get one, you can just make a reduction, and I'll talk about this next time in a lot of detail, from a NP complete problem to your new problem. Show that your new problem's harder than this one. Then it's got to be harder than all the rest. It's kind of like priming the pump. Once you get one, you can get more. But how do you get the first one? The first one, you have to show that any problem at all in the whole world that can be solved in non-deterministic polynomial time can be reduced to a sequence of Boolean formulas, or can be reduced to a bunch of tiles in a tiling problem. How do you do that? You need some way of representing a program in its complete generality. Remember, we did that with a decision tree? We only did that once the whole year. We did it with a decision tree. Decision trees are too weak to model programs in general. So how do you model a program in general? You introduce a whole fancy idea called a Turing machine, which is an abstraction of a program. And you specify what it means for a Turing machine to run in a certain amount of time. And then you mathematically construct these Turing machines. And then you prove. You give me any Turing machine that is a particular program that runs in non-deterministic polynomial time, and I'll show you how to convert that Turing machine. It's just a mathematical structure. It looks a little bit like a finite state machine. I'll show you how to take that and turn it into a formula. And this formula will be true whenever your machine solves that problem, and the formula will be false whenever your machine doesn't solve that problem. So that reduction is a general reduction from any program in the whole world. And if you're thinking, gee, that must be hard, you're right. And if you're thinking, gee, that must be ugly, you're doubly right. The proof is long, it's tedious, it's filled with details. We will not do that proof, not in this class or in the other class. But it's in every text somewhere, and it's softened up because it is hard to read. You can imagine. You have to take any program at all and convert it to a formula and describe the process in general. It's hard. But that's how you get the first one.
So the first ones weren't proved in the same like empirical test everything way. They're proved in general.
Right.
It has to be.
They were proved in these long, complicated papers. But once you get that, then you don't have to do that ever again. All right. The last thing. We talked about non-deterministic algorithms. Second thing, last thing. I want to at least leave you with a problem that's very intuitive that I want you to think about how to do it in non-deterministic polynomial time. Quick one, Hamiltonian circuit. How do you do it in non-deterministic polynomial time? You guess a path, and you check to see that there are edges between all the nodes. Guess a sequence of nodes, there are n nodes, make a permutation, guess it, and check if there are edges all the way through. The checking is done in linear time, the guessing is done in linear time, and that's your whole algorithm. In reality, you have to check them all n factorial possibilities, but you get them all in parallel. So you get it for free. Non-deterministic algorithms are magical. You can do a lot with non-determinism. Here's something you can't do. I give you a picture of a chessboard, say the initial position, given a position, and I ask you, does the person who is white and who's going to move next win this game? How would you solve that problem? You try all the possible moves for white, you try all the possible moves for black, you try all the possible moves for white, and sooner or later at the very bottom, you get all the final positions. And you see, if there's always a way for white to make a choice when it's his turn, that arrives at a position that checkmates black.
That would be can white.
Can white win with best play in this position? That's a long algorithm. It's exponential like crazy. You have to generate this whole tree. It's kind of like what you did for the Same game. And when you're all at the bottom, you decide whether you win or not. How do you do that problem non-deterministically? It turns out that you can't do this OR trick. Because if this move or this move or this move or this move works for white, that's all OR. But now I'm at the next level, and my opponent moves. So say I check that this move works for me. Now my opponent's ready to move. He's got 8 moves. I got to check all his moves and his moves together, because he could take any choice he wants. And I got to check that all of them end up with me in a checkmate. So I have to do OR for my moves, but AND for his moves. So I can't do those branches in parallel. Those branches I actually have to go ahead and generate sequentially. So the non-deterministic algorithm completely fails. And those problems, and generally two-person game problems, they're out here. They're outside of the NP-P category. They're even harder. A lot of them, the next class out here is called P-space, polynomial space. You can solve that problem in polynomial space, but you can't solve it in non-deterministic polynomial time. We're getting a little bit ahead of ourselves, but the problem is out here in the twilight zone. And it's P-space complete. Checkers is P-space complete. Go is P-space complete. These problems are much harder than just the NP-complete problems. As far as anybody knows, there's no good way to solve them. All right, let's quit today. Today was meant as kind of a general get a feeling. I'm going to start from the very beginning with this stuff, step by step, and do very specific examples next time to keep everybody up to snuff with this. This is hard stuff.